Okay, good morning. Okay, in the previous class, we discussed what is DFS algorithm, how it will work. Okay, okay. We take an example. Uh, in this example, okay, then we worked on it. Okay, okay. So next, we are moving to the strongly connected component concept. Okay. So, what is a connected component? Uh, how can find the strongly connected component? Okay. So, the definition. What is the definition of strongly connected component? The definition is and this is the definition. A strongly connected component of a directed graph G, where graph G is equal to V comma E. V is the tuples. V is the vertices. Is a maximal set of vertices C subset V, that for every pair of vertices U and V in C, we have a path U to V and V to U. That is, the vertices U and V are reachable from each other. Then a graph that satisfies this is called a strongly connected component. Okay. For example, we can consider this node B and this node F. Okay. It is possible to reach from B to F through this path or through this path. I can reach here. Also through this path I can reach here, no problem. There are several paths to reach from B to F. Okay, but from F, okay, but from but F, I can't go back to B. You can note here from F, I can't go back to B. Okay, I can't go back to B. Okay, you can note. Suppose this is the only outgoing. Suppose I move to here, then this is the only outgoing. I move to here, but this is an incoming, so I can't follow this path. Okay. Similarly, I can't follow this path. So from F, I can't reach B. So B and F should not be part of a connected component. Okay. So B and F should not be a connected component. Okay. Try to understand this concept. Okay. What is connected component? If there are two vertices, there should be a way to reach from one to other and from other vertex to this. Okay. So now you can consider this. Okay. For example, and considering another vertex. Okay, 1 minute. Sorry. Suppose I am considering B and E. Okay, B and E. Then you can note here it is possible to reach from E to B. B and E, if you consider B and D vertexes, it is possible to reach from E to B ED. Okay. It is possible to reach from E to B, B to and B to E through this one. So these are B and E are connected combo. B and E are B vertex and E vertex are part of a connected component. Okay. So this is the concept connected component. Okay. So this definition and example I discussed. So what is a connected component? An example. Okay. 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 So I'm discussing. Next I'm discussing how can find the connected component using an algorithm. Okay. So this is the algorithm we want to use. So this is called strongly connected component algorithm. Strongly connected component algorithm. Okay. So in the first step, first we want to perform a DFS. We know what is DFS. Perform DFS on the graph G. Okay. And compute the finishing time U dot F of each vertex. Okay. Note this. We want to compute the finishing time of each vertex in the graph. Okay. Okay. So we know that concept now. Okay. After DFS, we know how to compute the finishing time of each vertex. Okay. Then second step, I want to compute G transpose. G transpose is the transpose of the graph G. Okay. So it is possible by in this way. For example, suppose this is an example. In the first step, I will compute the DFS. Okay, you can note here 16 is the finishing time of B. That is, we finished 16 at first. Okay. Okay. So you can note that. So DFS is performed. Then we will find the transpose. Okay, G transpose. This is G transpose. How G transpose? It's very simple. Just reversion of edges. Okay, you can note here. This is in this, but at the same time, this is in this way. Okay. By reversing the direction of the edges, we will get the G transpose. Okay. Then we want to perform. You can go to the algorithm. In the second step, we calculate the G transpose. And in the third step, we will call DFS in, but with G transpose. Okay. We want to perform the DFS again with G transpose. DFS on G transpose. But what is the change? Okay. So, but in the main loop of DFS or anywhere, but we should consider this while processing the vertex. We should process the vertex in this way on order of decreasing U dot F. Okay, we should process the vertex in this way. We should perform DFS, but we should in which order we want to process the vertex. That is, we should process the vertex in the order of decreasing U dot. Okay, so that is the point. Okay, then do it. And last step, we want to output the vertex. Okay. So now I'm going to this concept. You can note here, this is 16, which means B is the first finished vertex. Okay, that is, in this graph, finishing time of B is 16, which means the first finished vertex. Okay, so I want to perform DFS this vertex at first. Okay. Okay. So here the finishing time of B is, since B is the first finished vertex, I must want to perform DFS from that vertex. Okay. So performed DFS. So you can note here, this is G transpose and this is the G transpose, and I should start from here. Okay. This is the G and B is the vertex here. B is the last finished vertex. I should start the DFS from here. Then then to where I will move symbol DFS. Okay, perform symbol DFS concept there. Okay, so I started from here. Then where I will move. So I started from here. Okay, my question is to Masna, why taken B? Why I taken B?
Last
Masna?
finished vertex. Last finished vertex.
The last finished vertex is B. So I started from the vertex B. Then what I will do, Masna? I will what I will do? I will do a DFS from this vertex. Okay. So we know the concept of DFS. Okay. So from B, I will try to explore in this direction. Okay. Then I will give a time. Okay, etc. Then I will move in this way. Then I will finish this one. Okay. I'm not fully saying this, just to go through. This is the concept. That is from here. Okay. I move to A. Then I will give the time. Okay. Then I will go to A. From A, I will try explore. I reached E. Is it possible to explore from E again? No, because B is already. So B is finished. Then I will come back to A. Then A is finished. Okay. Then I will come back to B. This is finished. Okay. So I got a DFS tree. Okay. I got a TFS tree in this way. This is a DFS tree, and the green are tree edges. Edges I used for exploring. Okay. Or discovering. So this is the tree edges, and surely this edge is part of the here. I will not use it for visiting. Okay. So this is the DFS tree. This green mark at the from the DFS tree. Okay. So this is one connected component. Okay. Now my next question is, from where I will start next? Devika. I started from B and performed DFS, and I got a DFS tree. Okay. Devika, from where I will start next DFS? Devika. Anugrah. Devika, Anugrah. Attendance തരൂല. ദേവിക റിപ്ലൈ ചെയ്ത.
സോ സി അല്ലേ?
Which one is finished at first? Why? Because finishing time of C is the greatest of them. Okay. So we will, as Anugrah told, we will start from C and again perform DFS. Then we will get a tree like this. This is another BFS tree. Okay, C and D only will be there. Okay. Now my next question to Devika. This is the second DFS tree. This is the first DFS tree. Then my questions to Devika. Devika, Devika, Sangeet Unnikrishnan.
Sir,
Devika പറഞ്ഞ്. From where I will start next?
sir,
I want
CP
to
or
perform DFS. C already finished. I performed DFS using C. Okay. I performed DFS using C.
B?
This is finished. Okay. Next, we want to consider these three only. Okay, these three, of which is having the which is finished at first. There we go. It is G. Okay, it is G because G is finishing time is 7. Okay, so it will be the last finished one. 7, 6, 4. So 7. So again we will perform DFS and we will get a small tree. Small DFS tree. Okay. Small DFS tree you can note here. I will reach here. Then I will come back here. Okay. So that is finished. This is another tree. Third DFS tree. Okay. So basically this is the third connected component. This is the first connected component. This is the second one. This is third one. And the last one is only, this is the single vertex. Okay. 4. Okay. Only one vertex is there, H, and we will perform DS then only. Okay. So these are the 4 connected components in this graph. Okay. So this is the method. If we needed, we can write in this way. Okay. You can observe the diagram C. That is, we can write in this way. CD is a connected component. So we can write C and D together. Okay. Then AB is a connected component. AB is together. FG is a connected component. FG here. H is a connected. Then we can we connect in this way. Okay. So AB is connected to CD. Okay. AB is connected to CD. And you can note the direction. Here the direction is given in this way. Okay. You can note that AB is connected to CD. AB is connected to CD. And the direction is, we can note the direction. Okay. The direction is actually our DFS tree. Okay. Okay. This is the direction. Okay. This is G. This is G. We should use that direction. Okay. Okay. Note that point. We should use the direction by referring the graph G. Okay. Not a G transpose. Okay. Then the direction is this way. Similarly, CDFG means CD is here, FG is here, and CD to FG direction is there. You can note that. CD to FG. CD to FG. This is the direction. Okay. In this way, we can write this also. Okay. So this is the method of finding the connected components in a graph. Okay. Or strongly connected components in a graph. Basically, this is an application of our DFS algorithm. That is, this is an application of DFS algorithm. Okay. So, okay. Next, we need to solve this problem. Find strongly connected component of digraph using the algorithm and showing each step. This is a university exam question and it's asked in April 2018. Okay. So, a graph is given. Okay. I'm not solving it now because already I discussed this concept and just you taken it as a homework. Okay. and solve it by yourself. It is a very simple problem basically. Okay, so what should be our steps? uh, I will ask you the question. Sangeet Unnikrishnan, Sangeet, just explain the steps. Okay, just explain the steps involved in solving this problem. Sangeet, Sangeet, Sangeet present അല്ലേ? Sangeet.
Hello.
Sangeet.
Hello.
Okay, Sangeet. I just want to hear
Hello.
the steps only. Okay.
Hello, sir. Hello,
Sangeet.
sir.
Okay.
Hello.
What is the first step?
Hello,
This
sir.
is graph G. Okay. Okay, Sangeet. പറഞ്ഞോ. This is graph G. What is the first step? We should
Hello.
perform DFS. Okay, we should perform DFS and find the finishing time of each vertex. Okay, Sangeet. So we can start from any vertex. Okay, I can start from 1, then find the finishing time of the vertex. Then after that I can take, for example, suppose I started from 1. Okay, then I will try to explore from, I will reach here, then I will reach here. Okay, so this is 1, this is 2, this is 3. Okay, then I will finish this one at first, 4, then I will go back, then I will finish this 5, then I will go back, then it is 6. Okay. So after this I started from 1. Okay, so the finishing time of 1 is 6. Now this is basically a BFS tree, sorry, DFS tree. Okay, this is a DFS tree. Okay, then arbitrarily select any other vertex. Okay, there are still unprocessed vertexes 9, 6, 3, 8, 2. I can select any of the vertex. Okay, that is the difference between DFS and DFS. Okay, so suppose I started from 9, I can start from 6 also. Suppose I started from 6. Okay, then this is 7. Okay, 7, then I will move to 9. This is 8. Why I return 7? Because 6 I finished here. Okay, then 7, then move to 8, explored, then I okay, then I move to here 9. Okay, then I tried to reach 6 back, but it is already finished. Yeah, so what I will do, I will finish 3, 10, then I will go back to 9. Now it is 11, so also I finished. Okay, then I will go back 12. Now this is another, you can note here, another, this is another DFS tree. Okay, so you can note the starting finishing time. Okay, next I will start, suppose I started from 8, then what I will do, I will give it time 13. 1 minute. 1 minute. Then I will start from, suppose I started from 8. Okay, I will, time is 13. Okay, discovered time is 13. I will move to this here. Now it is 14. Then I will move to 2. Then it is 15. Then I will try to explore from here, but it is already visited. Okay, so I finish it at first. 16, then it is 17. Okay, then it is 17, then it is 18. Okay, this is the DFS after performing. Okay, anyway, I explained this. Now, what is the next step, Sangeet? Find the G transpose. Okay, Sangeet, what is the next step? Find the G transpose. Okay, Sangeet. Hello, Sangeet. Okay, what is the next step? Find the G transpose. How can find the G transpose? Devika. How can find the G transpose? How can find G transpose, Devika? Devika, please. Anugrah. Anugrah. How can find G transpose? By reversing the direction of the edges. Then, okay, G transpose I will find. Then what should be the next? I want to perform DFS on this graph. Okay, DFS that you should complete. DFS on G transpose. But what? Who should be the starting vertex? Anugrah. Who should be the starting? Which vertex you should take? Because the finishing time, you can note the finishing time. Here we finished at first. Anugrah, which is finished at first here.
Hello, sir.
Which is finished at first.
Eight.
Anugrah, this one, okay. Oh, sorry, this one. 18. So we should start from 8. Okay. Then perform DFS. Okay. Then you will get a strongly connected component. Okay. Then where I will start. Then I will start from 12. Okay. From here I want to start. Then do it. In that way you should proceed. Okay. Please take it as a homework and do it. Okay. 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 Okay, now we discussed the strongly connected component finding method and the university questions relating to that topic. Okay, now we are going to the concept of another concept. Okay, what is minimum spanning tree? Okay, so now I'm moving somewhat faster. What is minimum spanning tree? Okay, so this is another concept. Next concept is minimum spanning tree, okay, or MST. Okay. Okay. Now I am starting next topic, minimum spanning tree. Okay. Minimum spanning tree. Okay. MST. Okay. So what is MST means? This is the definition of MST. I'm trying to simply define what is MST. Okay. So basically we perform MST, usually we will perform it on a graph. Okay, suppose this is a graph G, and vertex is there, edge is there, and this is weight, etc. Okay, so we will perform a GFS, we'll perform a MST on a graph G, then we will get a tree. Okay, so the resulting will be a tree. So what is the difference between tree and a graph? What is the difference between tree and a graph? Anyone? So basically, tree is called an acyclic graph. Okay. Tree is called an acyclic graph. What its meaning? There should be no cycles. Okay. Basically, a tree is a graph, but it's acyclic. That means there should not be any and there should not be any loops. Okay, there should not be any cycles in the graph. Then that is called an acyclic. Then it is called a tree. Okay, so what is minimum spanning tree means? Perform a traversal on the graph and we will get a tree. Okay, then we will get a tree. Okay, now what is a minimum spanning tree? A minimum spanning tree or minimum weight spanning tree is a subset of the edges of a connected edge weighted undirected graph that connects all the vertices together. These are the properties. We will perform it on a graph. Okay, we will perform it on a graph. Then we will get a tree. Tree means there should not be any cycles. Okay, then we will get a tree, and it is a minimum weight spanning tree. Minimum weight spanning tree. Okay, it is a subset of the edges connected. It is a subset of the edges connected. Then subset, you can note here, it is a subset of the edges connected. Next, edge weighted undirected graph. It is an edge weighted undirected graph. Okay, the edges are weighted. And that connects all the vertices together. This is another property. It should connect all the vertices. Okay, it should connect all the vertices, and there should not be any cycles. Without any cycles, then only we can say it is a tree. And with minimum possible total edge weight. Okay, so the last point saying is the edge weight, the total edge weight in the tree should be minimum. Okay, so a tree that satisfies all these properties is called a minimum spanning tree. Okay, so what is a minimum spanning tree? A minimum spanning tree is a subset of the edges of a connected graph. Then it is an edge weighted undirected graph that connects all the vertices together without any cycles and with the minimum possible total edge weight. Okay, for example, this is a graph. Okay, so which are the edges? How many edges are there? 1, 2, 3, 4, 5, 4, 5, 6, 7, 8, 9, and 10. Okay, there are 10 edges, but after performing DFS, after performing or after finding the spanning tree, it consists of these edges only. 1, 2, 3. These are undirected edges also. Okay, these edges only, and these edges, that is, it is basically a subset of our graph edges. That is, initially we have a lot of edges, but in the spanning tree, it should be a subset of the edges in our graph. Okay, so okay, then next property is these edges should connect all vertices. Okay, you can note here all vertices are covered. This covered, this covered, this covered. All vertices are covered. Okay, it should cover all vertices. The tree should include all the vertices. Okay, and the next property is the weight should be minimum as possible. Okay, it should cover all the vertices with a minimum weight. You can note here, and these are the weight: 8, 8, 5. You can note the weight. And the summation of these weights should be minimum as possible. That is the last property. Okay. Okay. So these are the properties. Okay. These are the properties. Okay. You can use this as our definition. No problem. Okay. Just go through it. You will get an idea. And this is an example. Okay. In order to find the minimum spanning tree, we can use two algorithms. One is called Kruskal algorithm. Okay, there are two algorithms we can use to find the minimum spanning tree. One is called Kruskal algorithm, and another is called Prime's algorithm. Prime's algorithm. So, minimum spanning tree can be found using two algorithms. One is called Kruskal algorithm. First, we will discuss Kruskal algorithm. Okay. Then another is algorithm. Okay, Prim's algorithm that we will discuss after discussing Prim's Kruskal algorithm. Okay, Prim's. Okay. So this algorithm, after performing it on a graph, will produce a minimum spanning tree. Okay. That should satisfy all the properties mentioned here. Okay. Okay. Anyway, we can discuss that Kruskal algorithm on the next classes. And this is one of the, it is very simple. Okay, basically it is, the concept is simple. Then spanning Kruskal algorithm. Then after the next class we will discuss Prime's algorithm also. Okay. Okay, thank you. We can discuss that in the next class. Okay, tomorrow. Okay, please give attendance. I will call, and please give the attendance. Okay. Okay, Akash, Rajiv. Okay, thank you. Sorry, Abhinand absent. No? Abhinand absent. No? Okay. Abhinav, Adarsh, Advaid. Abhinav, Adarsh, Advaid. Okay. Ajmal, Agilsi, Anaka. Ajmal, Agilsi, Port, Anaka. Okay. Anjali, Anugrah. Anjali, Anugrah. Okay. Adinanil, Adulpike, Devika T. Adinanil, Adul PK Devi. Adul absent. No? Adul PK Devika T. Dilna, okay, Masna, okay. Jasna Karthike Kirtana. Jasna Karthike Kirtana. Karthike, okay. Sinan Ijas Nafai. Sinan Ijas Nafaike. Nafaike, okay. Neha ke Nitin Babu. Neha ke Nitin Babu. Neha Nitin Babu. Neha absent. Neha absent ഇടുന്ന Neha. Nitin Babu. Nitin Babu. Okay. Pranave ഇപ്പോഴും ജോയിൻ ആയതാണോ? Pranave. Okay, Pranave. Pranav C. Pranave C. Pranav C. Neha present ആണോ? Neha absent ഇടട്ടെ. Neha. Okay. Pranave C. Pranave absent ഇട്ടിട്ടുണ്ട്. Pranav C absent. Okay. Raisa Khalid. Raisa present ആണോ? Okay. Okay, Pranav C present ആണോ? Okay. Okay. Raisa Khalid. Rasana Nihala Riswin Nivan. Rasana Riswin. Riswin present ആണോ? Riswin. Sahala. Roshan TP Sahala B. Roshan TP present ആണോ? Okay. Sahala B present ആണോ? Sahala B absent ആണോ? Okay. Sahala and Sangeet Sarang Sharun Shraddha. Sangeet Sarang Sharun Shraddha. Okay. Vishnu Vinod Vaishnavi Baby Srishma.
Present, sir.
Vishnu Vinod Vaishnavi Baby Srishma Anjita. Okay. Okay. Anjita Shirona. Okay. Okay. അപ്പോൾ ആബ്സെൻറ്റീസ് പറയുന്നത് നേഹ ആബ്സെന്റ് ആണ്. നേഹ പ്രസന്റ് അല്ലല്ലോ. സഹല ബി ആബ്സെന്റ്. ഓക്കെ. ലെഫ്റ്റ് അയക്കാം. നിങ്ങൾ അറ്റൻഡൻസ് തന്നവർ ലെഫ്റ്റ് അയക്കും. Neha, Sahala B, Pranav A, Pranav C ഉണ്ട്. And then Babu. Okay, thank you. Thank you.